Hello everyone, good day. I am BSED Teric and today we will be going to talk about Chapter 30 about inductance. So Chapter 30 introduces one of the most important circuit elements in electrical engineering and physics, the inductor, also known as a coil. An inductor is a passive electrical component that stores energy in a magnetic field when current flows through it. The concept of inductance extends the idea from chapter 29 on electromagnetic induction by examining what happens when the same circuit that produces changing magnetic flux is itself subject to that changing flux. So this self-referential behavior creates fascinating phenomena. Inductors resist changes in current. They store energy magnetized as capacitors store energy electrically. And when combined with capacitors, they can produce oscillating circuits that form the basis of radio transmitters, filters, and countless other electronic devices. Understanding inductance is crucial to analyze which power most modern technology. This chapter develops from foundational concepts to increasingly complex circuits and phenomena. We begin with mutual inductance, how changing current in one coil induced EMF in a nearby coil, and then move to self-inductance, how a coil induced as an EMF opposing changes in its own current. We learn to calculate energy stored in magnetic fields and analyze the behavior of circuits containing inductors with resistors, or the RL circuits, and with capacitors, RC and LRC circuits. The mathematical treatment reveals deep analogies with mechanical associations, showing how electromagnetic phenomena obey similar differential equations as mechanical systems. By chapter's end, we understand what oscillating LC circuits are the heart of wireless communication, that resistive damping in L to R to C circuits explains real-world decay of oscillations, and that inductance is as fundamental to electrical engineering as resistance and capacitance, inductor L, the capacitor C, and resistor R. Before we proceed to our main discussion, let us first know our learning goals for this chapter. So we are looking forward at first how a time varying current in one coil can induce an EMF in a second unconnected coil. Second, how to relate the induced EMF in a circuit to the rate of change of current in the same circuit. Third, how to calculate the energy stored in a magnetic field. Fourth, how to analyze circuits that include both a resistor and an inductor or the coil. Then the last one is why electrical oscillations occur in current that include an inductor and a capacitor. So let's begin with a familiar real-world example to make inductance easier to understand. Traffic-sensitive lights that change when a car approaches an intersection. As you can see in the setup used at intersections, this system demonstrates mutual inductance in action without any direct electrical contact between the car and the sensing system. Beneath the street is a large coil of wire carries an alternating current, creating a continuously changing magnetic event. When a car made of conducting metals passes over the coil, the changing magnetic field induced eddy currents in the metal of the car. These induced currents produce their own magnetic field, which then interacts with the magnetic field of the wired coil. So, as you can see here, this interaction allows electromagnetic energy to be coupled between the coil and the car. Sensors connected to the coil detect This changes and sends signal to the traffic light system, causing the light to change. This example shows that mutual inductance is not just a laboratory concept, but an essential part of everyday infrastructure. This real world example prepares us to study inductance more formally. As you can see from this application, electromagnetic coupling can occur across space and through materials without direct wire connections. The strength of this coupling depends on factors such as the geometry of the coils, their proximity, the frequency of the alternating current, and the properties of the materials involved. As we move through this chapter, we will learn how to describe the interaction quantitatively using mutual inductance, VM, and how to predict how much EMF is induced in one circuit when the current in another changes. So as you can see, inductance is not something to avoid but a phenomenon engineers deliberately control. Understanding inductance allows engineers to design systems for wireless power transfer, efficient power transmission, electromagnetic braking, and other technologies that rely on invisible electromagnetic coupling between circuits. So mutual inductance describe how two nearby circuits influence each other through magnetic field. When a charging current flows in one coil creates a changing magnetic flux that passes through a second coil, inducing an EMF according to Faraday's law, the constant that relates the induced EMF in coil 2 to the rate of change of current in coil 1 is the mutual inductance, written as epsilon 2 is equal to negative m times 1 over dt. By reciprocity, the same m applies if the rows of the coils are reversed, or the epsilon 1 is equal to negative m times d the I sub 2 over dt. The value of m depends on the coil size, number of turns, orientation, distance, and the material between them. Coils that are close and well aligned have a larger mutual inductance. The unit of mutual inductance is the Henry. 1 Henry can be written in several equivalents form, like we have the 1H is equal to 1 WB over A, or the Weber per ampere, or the 1 volt times second per ampere, or the 1 ohms or 1 joules per ampere squared. So in practice, most coils have mutual inductance in the millihenry or microhenry range. Mutual inductance is the key principle behind transformers, where energy is transferred efficiently between a primary and a secondary coil at different voltage without any direct electrical connection. Mutual inductance can be defined in two equivalent ways. From Faraday's law, we have the M equals the phi 21 over I1, where phi 21 is the magnetic flux through caused by the current I1 in the coil 1. Then this shows that M measures how much magnetic flux is linked between the coils per current from the induced EMF viewpoint. M is equal to negative epsilon 2 over di1 over dt. The minus sign in epsilon negative m or minus m over or the close of minus di over dt reflects Lenz's law, meaning the induced EMF opposes the change in current. In practice, m is calculated from the coil geometry, number of turns, separation, and the magnetic permeability of the material between them. Practical and elegant application in mutual inductance is the wireless charging electric brushes. The brush base contains a coil connected to alternating current from the wall socket, typically 60 hertz in North America or 50 hertz in Europe. So the toothbrush itself has no direct electrical connection to the base but contains a second coil and a battery charging circuit. When the charge to when the charger toothbrush is placed on the base, the AC current in the base coil creates a time varying magnetic field that links with the coil in the toothbrush. This changing magnetic flux induces an EMF in the toothbrush coil according to Faraday's law. So Faraday's law, we have the epsilon is equal to negative m times di over dt, where m is the mutual inductance between the base and the toothbrush coils, and di over dt is the rate of change of current in the base coil. The induced EMF drives current through a rectifier circuit which converts AC to DC, which charges the rechargeable battery inside the toothbrush. This system is elegant because there is no danger of electrical shock, unlike electrical connection. No moving contacts to wear out, radically broken when the toothbrush is removed. The mutual inductance drop to zero when the coils are far apart. Now let's have a problem solving. So in section 30.1, mutual inductance, we have two coils have mutual inductance M is equal to 3.5 times 10 to the power negative 4 H or Henry. The current I in the first coil increases at a uniform rate of 130 ampere per second. A. What is the magnitude of the induced EMF in the second coil? Is it constant? And B. Suppose that the current described is in the second coil rather than the first. What is the magnitude of the induced EMF in the first coil? So let us first identify the given. We have mutual inductance and rate of change of current, as you can see here. Next, we have for mutual inductance, a change in current in one coil induces an EMF in the other coil. So the formula for induced EMF due to mutual inductance is E is equal to induced EMF, where M is equal to mutual and di over dt rate of change of current. Then the negative sign indicates direction of Lenz's law, but we we are asked for magnitude, so we just gently ignore the sign. Then after that, we need to write the formula. So as you can see, the magnitude only. Then after that, we need to substitute it. Substitute the values. Then after substituting the values, we need to calculate it. Then the answer would be the 0.270 voltage. So is it constant? Yes. It is because the current in the first coil increases at a uniform constant rate. So the induced EMF in the second coil is also constant. Then for the part B, or the induced EMF in the first coil, we have this situation where the two coils have mutual inductance of M is equal to 3.25 times 10 to the power negative 4H. The current I in the first one, I1 in the first coil increases at a uniform rate of 830 830 ampere per second. So the question here for the B is suppose that the current described is in the second coil rather than the first. What is the magnitude of the induced EMF in the first coil? So as you can see here, we have these the given for the part B, where the mutual inductance works both ways. If the same rate of current change occurs in the second coil, the induced in the first coil has the same magnitude. So we are going to use this formula, use the same formula. Then, as you can see, we are saying, then after that, all we need to do is to substitute the same values. So we need to substitute the values in those in the part A values, then or in this given in the given situation. Then after that, let's calculate this. The 3.25 times 10 to the 1 negative 4 times 830 is equal to, the answer is 0.27 voltage. So to answer this problem shows that mutual inductance is symmetric. A changing current in either coil induces the same magnitude of EMF in the other coil, provided the current is the same. The induced EMF is constant here because the current changes at a constant rate. So self-inductance, usually called inductance, describes how a single coil interacts with its own changing magnetic field. When current flows in a coil, it produces magnetic field that links the coil's turns. If the current changes, this changing field induced an EMF in the same coil that opposes that change. This is given by epsilon sub L equals minus L g dt, where L is the self-inductance and di over dt is the rate of change of current. Self-inductance is also defined as L equals phi d over I, where phi v is the total magnetic flux link with a coil carrying current I. Like mutual inductance, L is measured in henries. It depends on the coil's geometry, number of turns, and magnetic permeability. Coils with more turns or iron cores have much larger L. So self-inductance is what makes inductors useful in circuits because of the minus sign in epsilon 1. L is equal to subscript L is equal to negative L times d1 over di over dt. Inductors oppose rapid changes in current and act as current smoothers. When a switch is closed, the current increases gradually instead of instantly. So this property protects circuits from sudden surges such as voltage spikes from lightning in power lines, where large inductors limit dangerous current changes. So inductors also smooth ripples in power supplies and control current changes in radio and communication circuits. A larger L means stronger opposition to a larger current, which is why large Iron core inductors or mini Henrys are more effective than small air core coils or the micro Henrys. While in lightning strikes on electrical power transmission system presents a critical challenge to maintaining system reliability and protecting equipment from damage. So a typical lightning bolt carries a current of 10,000 of amperes, strikes in a microsecond or less. So this extremely rapid current change creates an enormous voltage, or the V is equal to L times di over dt, where the tiny time interval dt and huge current change di combine to produce voltages exceeding hundreds of thousands of volts. Such voltage spikes can destroy transformers, circuit breakers, and other if not controlled. Power systems address this danger by incorporating large inductors at strategic locations in the transmission network. These protective injectors are designed to have significant self-inductance, often in a range of 1 to 100 henries, so that when lightning strikes, the inductor produces an opposing voltage that limits the rate of current increase, instead of allowing the current to rise from 0 to tens of thousands of amperes in microseconds. The inductor forces the change to occur over a longer time scale, or in milliseconds rather than the microseconds. So this extended time interval dramatically reduces the peak current and voltage, protecting downstream equipment. So moving on, in the inductors as current elements, we have this um, in an inductor behaves differently from a resistor in a circuit. So the voltage across it depends on how fast the current changes. So we have the V sub L equals to L times D over dt, not on the current magnitude itself, like V is equal to IR. If the current is constant, or the di over dt is equal to 0, the conductor acts like a short circuit. If the current change just rapidly, even a small current can produce a large voltage. This contrasts with resistors where voltage increases directly with current. So in the inductor voltage formula, we have the V is equal to L over D times Ti over dt is K for analyzing as transient or time varying currents, I mean circuits. So in AC circuits and inductors, impedance is Z sub L is equal to omega L, where the omega is the angular frequency in radians per second. So impedance rises with frequency. So inductors oppose high frequency current more than low frequency or the DC currents. This property is used in filters. Inductors block low frequency in high pass filters, and capacitors pass low frequency in low filters. The voltage current relationship guides analysis of R, L, and LC and complex circuit. In a potential across a resistor, so a resistor is a voltage depends directly on the current. So we have these V sub R equals I IR. Then where V sub R is the voltage across the resistor, while I is the current. So, and R is the resistance, is in ohms. So, voltage drops occur in the direction of current. If current is constant, voltage is constant also. So, power dissipated is P is equal to I squared is equal to V squared over R. Loss as heat. Resistors are passive, unlike inductors, which reacts to change in current. So voltage across a resistor can be written as V subscript AB is equal to V subscript A is equal to negative IR, following the Kirchhoff's voltage law. So the VI relation is algebraic. So resistive circuits are simple. We have the I is equal to the V over R, or the current is equal to V over R. In contrast, inductors and capacitors involve derivatives because their voltage depends on the rate of current change, adding complexity but enabling energy storage and frequency dependent behavior. When the current is constant, the voltage across an inductor is 0. So V subscript L is equal to L di over dt is equal to L times 0 is equal to 0. Unlike a resistor, the V subscript R is equal to IR. An inductor with steady current acts like a short circuit. In DC circuits at steady state, inductors can be replaced by shorts for analysis. At the moment a switch closes, T is equal to 0, the inductor opposes sudden current changes, acting like an open circuit, then gradually becomes a short as current stabilizes. Inductors store energy rather than dissipate it. Power in a steady current inductor is P is equal to V sub L times I is equal to 0 times I is equal to 0. So while energy stored is U is equal to 1 half Li squared, initially the inductor resists current rise. So V subscript L opposes battery voltage. Then voltage decreases as di over dt decreases. At steady state, di over dt is equal to 0 while V subscript L is equal to 0. The resistor sees V subscript R is equal to IR and the inductor stores constant energy without dissipation. So for the potential across an inductor with increasing current, so we have the when current increases to a di over dt greater than 0, the inductor develops a voltage of V subscript L is equal to L di over dt that opposes the change. If current flows from A to B, then after that the V subscript A is less than V subscript B, opposite to a resistor of V subscript A is greater over B subscript B. A larger inductance L or faster change to di over dt produces a larger opposing voltage. So this voltage represents energy being stored in the inductor's magnetic field. In an RL series circuit, when a switch closes, the inductor initially opposes most of the source. As current rises, di over dt decreases and voltage across the resistors increases. So for a series of R to L circuit with battery voltage V, resistor R and inductor L at T is equal to 0. Current is 0. di over dt is larger and V subscript L is equally to V, somewhat equally to V current, then the rises exponentially toward the I is equal to V over R with the constant tau equals L over R. So larger L slows the rise, larger R speeds it during the transient energy stored in the inductor grows. So we have the U equals to 1 half over L is Li squared. So at this steady state, the T will become in the infinite, or the current is constant I is equal to V over R, V subscript L is equal to 0, where V over subscript R is equal to V, and the stored energy is U is equal to 1 half L over V over R squared. And then moving on, we have this potential across an inductor with decreasing current. So when current to an inductor decreases, the di over dt lesser than 0, the inductor produces a voltage rise. V subscript L is equal to L over dt, L dt over di over dt. So that opposes the decrease. Then if current flows from A to B, then V subscript A is lesser than V subscript B, creating a back EMF that tries to maintain current. Magnitude is V subscript L is equal to L times the absolute value of di over dt. So a fast decrease in a large inductor produces a large voltage spike. This is why opening a switch with inductive current can generate dangerous back EMF. When a switch opens, the inductor's back EMF can damage components or cause arcing. So protective devices like number circuits or flywheel diodes provide a path for current to decay smoothly. The inductor discharges and stored energy, like U is equal to 1 half over 1 half and times Li squared is dissipated as heat. So the decay follows the same time constant. Tau is equal to L over R as the growth in current. So in AC circuit, these produce sparks if no controlled path exists for the energy in the magnetic field. Then for the magnetic field energy, so an inductor stores energy in its magnetic field, like a capacitor stores energy in its electric field. Then the energy stores is U is equal to 1 half over L squared, Li squared. Then depending on L in inductance in henries and I and in current in amperes. So energy is stored when work is done to increase current against the inductor's opening voltage and released when current decreases. So unlike resistor, E equals I squared R that dissipates energy as heat, an ideal inductor stores energy without loss. Real inductors have small resistance, so some energy eventually dissipates, but inductors are fundamentally storage devices. So this makes them essential in power system for smoothing power, storing energy during the low demand and releasing it during high demand. So large generators can store megajoules of energy in their magnetic field. In the magnetic energy density, capacitor stores energy in its electric field. The U is equals 1 half epsilon naught E squared, and inductor stores energy in its magnetic field. Energy density, or the U sub m, is energy per unit volume, measured in joules per cubic meter. For a uniform magnetic field, U sub m equals b squared over 2 m e naught, where b is a magnetic field strength or Tesla's, and the m e naught is the permeability of free space, or the 4 pi times 10 to the power negative 7 Tesla times m over a, where the total in charge in an inductor is U is equal to the integral of U sub m gv equals integral of b squared over the m u naught dv, or approximately in this formula. So stronger fields and larger volumes store more energy. Magnetic material of permeability, or the mu equals key sub m, or the mu naught, the micronaut, the energy density becomes u subscript m is equal to b squared over 2 to not the micro although the key subscript m appears in the denominator, the magnetic field B is stronger in the material, increasing total energy storage. So this is why iron core inductors store more energy than air core coils of the same size and current. Energy density helps design high power inductors, manage heating, mechanical stress, and magnetic radiation, and is critical in superconducting devices carrying very high currents. Then, for the RL circuit, combines a resistor R and inductor L with EMF source epsilon battery voltage. So two switches control the operation. We have the S1, the S sub 1, and the connects battery to RL closes circuit to build current for the S sub 2 bypasses battery disconnect source. So let's RL loop decay current. So top diagram is the S sub 1 close battery derives current through the RL from the point A to B to C. Bottom diagram, S1 opens S2, then close the RL combination forms closed loop without battery. So current decays through resistor alone. So inductor stores magnetic energy. When battery remove, inductors pushes current through R to avoid sudden stop. So time constant govern both growth from the S1 close and the decay in S2 closed. So tau equals L over the R. So these circuits model real-world situation like motors starting or stopping or relay switching. Then for the current growth in an RL circuit, we have the RL circuit with battery or epsilon voltage resistor R, inductor L switch for the S1, and S1 or the S sub 1 opens at T is equal to 0, connecting battery. So current cannot jump instantly from 0 to the final value, or the I sub F equal epsilon over the R. So inductors oppose sudden change. The current grows exponentially. We have the I times T is equal to I subscript F, then times 1 negative e to the minus T over tau. So approaching this steady state, I sub f asymptotically. Growth rate slows as increases. Inductor builds magnetic field opposing battery. So time constant or the tau is equals L over R. The time constant after 1 tau it reaches negative 60 degree. I mean this 60% of L sub F after 5 tau 90%. Graph shows I starts at 0, curves upward approaching the L sub F horizontal line. Steady state inductors act like short wire or the X sub L irrelevant for DC. So current flows steadily through the R. For the current decay in an RL circuit, we have the setup for the battery creates an initial the I nut flowing through resistor R and the inductor L. So has built up magnetic field storing energy. So at T is equal to 0, S2 or the S sub 2 to bypass battery or remove voltage source, leaving only the R and a loop. So no battery means circuit to wants current to stop. But inductors, magnetic energy keeps current flowing, slowly decaying through resistors. So current decays exponentially. Like we have the I of t equals I naught e to the minus t over tau, where tau is equal to L over R is the time constant. Graph shows I starts at I naught drops to 37% of I naught after 1 tau reaches 5% after the 3 tau. So energy U sub B is equal to 1 over, also open parenthesis, 1 over 1 half times all I squared dissipates as heat in air. So inductor doesn't want current to change suddenly. Self-induced EMF opposite. Then for the LC circuit or the oscillation for step 1 out of 4, we have this. In step 1, starts the oscillation cycle in an L to C circuit. We have this inductor plus the capacitor connected, no resistor. Then use battery or the V voltage and left hand switch to charge capacitor to maximum voltage or the V sub M, and charge Q charge Q sub M or the positive Q sub M on the top plate, and on the bottom plate we have the negative Q sub M on bottom, which opens capacitor holds full charge like charge the battery. So current is equal to 0. Through inductors, all energy stored as electric field inside capacitor. The U sub E is equal to 1 half CV sub M squared or 1 half Q sub M squared over C. Total circuit energy is equal to U sub E rather plus U sub B with U sub B is equal to 0. So no magnetic field yet. Diagram shows fully charged capacitor open switch, zero current, energy all electric. When switch closer, next step, capacitor discharges the inductor, starting oscillation cycle shown in this figure. Then for the step 2, the capacitors discharge through the inductor. Charges flow from positive to plate through coil to negative plate, then creating a current I that builds up from zero. So as capacitors empties or voltage drop, current is its rate of increase slows because less voltage drives it. So inductors build strong magnetic field B inside the coils, storing energy as current grows. So when capacitor voltage reaches zero or the fully discharged, the current reaches the maximum I sub m induced EMF in an inductor is now maximum, trying to keep the current flow. So the diagram shows empty capacitor, the maximum current I sub m flowing the right to left, peak the magnetic field B sub m, all energy. Now magnetic U magnetic U sub m is equal to 1 half over L I sub m squared. Total energy is equal to U sub m plus U sub E conserved. So electric energy depleted, magnetic energy maximum. Then the next step is inductor pushes current to recharge capacitor with opposite polarity. So in step 3, so from step 2, in inductor full of magnetic energy, maximum current flowing, the inductor starts emptying. So it collapsing magnetic field pushes charge onto the capacitor plate, but with opposite polarity, flip positive and negative compared to start. So you can see they're flipped. So voltage across capacitor builds to maximum V sub m with reverse polarity where the positive Q sub m on right plate and the negative Q sub m on the left. Current gradually decreases from the maximum to zero as magnetic field B fades. Eventually, current stops completely as I is equal to zero. So magnetic energy U sub B depletes to zero and capacitor reaches maximum reverse charge or the Q sub M. All energy now electric as U sub E is equal to 1 over Q sub M squared over C. So the total charge is E is equal to U sub E plus U sub E. U sub B plus U sub E conserved perfectly. So the diagram shows fully charged capacitor opposite polarity, zero current through inductor, zero magnetic field. So next, capacitor will discharge back through inductor. So flipping polarity again toward for the step 4. So think of the LC circuit like a ball bouncing between two hills. So the capacitor, the battery light as electric charge, and the inductor coil stores energy as the magnetic field. So step 4 shows the moment when the capacitor is completely empty, or full discharge, or the zero charge. So all energy has transferred to the inductor. Then, where maximum current I sub M flows and creates the strongest magnetic field B sub M inside the coil. Then the current now flows in the opposite direction from earlier steps, reversing the process. So soon after, the inductor starts emptying its magnetic energy, pushing charge back onto the capacitor, recharged to its original original voltage, returning the circuit to step 1. So this back and forth energy swap between electric capacitor and magnetic inductor storage creates endless isolation, like a pendulum swinging forever. Total energy, we have the is equal to U sub B plus U sub E stays constant, bouncing perfectly between magnetic U sub B and electric U sub E forms. So for the electric isolation in an LC circuit, so we know that an LC circuit is like a pendulum. So energy bounces back and forth between capacitor C stores electric energy at Q and inductor L stores magnetic energy as a current I flowing through coils. So apply Kirchhoff's law rule around the circuit. Sum of voltage drops is equal to 0. So and you get the same math equation as simple harmonic motion from chapter 14, like a mass on a spring. So charge on a capacitor isolate as Q times T is equal to Q cosine of omega T plus phi. So it starts maximum, swings to 0, reverses. Current through circuit it is equal to dq over dt is equal to I of t equals minus omega q q not sine of omega t plus phi. So the maximum when charge is 0. So angular frequency omega equals 1 over square root of LC. Its isolation speed depends only on L, or the inductance henries, and C, or the capacitance and farads. So as you can see here, then current travels clockwise, and then after clockwise, counterclockwise, creating an AC isolation. So no resistor means energy conserved forever, or ideally pure electrical pendulum. Then moving on, we have these electrical and mechanical isolations are similar because they follow the same basic of energy exchange. In a mass spring system, energy moves back and forth between kinetic energy due to motion of the mass and potential energy stored in stretched or compressed spring, causing the mass to isolate. In an inductor, capacitor, or LC circuit, energy also moves back and forth, but between electrical energy stored in the capacitor and the magnetic energy is stored in the inductor, causing the charge and current to isolate. So the mass in mechanics makes a role similar to the inductor in electricity. So while the spring is like the capacitor, so both systems isolate at a natural frequency, or the negative omega is equal to the square root of k over m for the mass spring system, and this omega is equal to 1 square root of LC for the LC circuit, showing that electrical and mechanical isolations follow the same mathematical rule. Then for the LRC series circuit, a charge of isolator is created in two simple steps. So first, when the S is in the top position, the battery or the EMF source or the E epsilon is connected directly to the capacitor C, charging into a maximum voltage or the what we call the V naught. Then and charge Q naught similarly to filling a bucket with water. So next, when the switch is moved to the bottom position, the battery is disconnected and the charge capacitor is connected to the inductor L, and resistor are in series. So forming in LRC loop with no battery. The capacitor then discharged through L and R, and energy moves back and forth between electric energy in the capacitor and magnetic energy in the inductor, oscillating at a frequency close to 1 over square root of LC, while the resistor slowly removes energy as heat, causing the isolation to gradually decrease in size. This behavior is called damp isolation and is similar to a mechanical system like spring with friction. Series circuit shows a damp harmonic motion when the resistance R is not too large, meaning that charge Q on the capacitor oscillates back and forth but gradually decreases in size over time. So this graph shows this as a sinusoidal wave. Those peaks slowly get smaller because some energy is lost as heat in the resistor. The oscillation happens because energy keeps transferring between the electric field of the capacitor and the magnetic field of the inductor, while the resistor removes energy from the system. So the speed of this oscillation is described by the angular frequency. The omega prime equals square root of 1 over L C minus R squared over 4L squared, as you can see there. So showing that the resistance reduces the isolation rate. So this behavior is the same swing that slowly comes to rest due to air resistance, making the motion oscillatory but fading with time. So we will try this another problem solving about the RL circuit. So the situation is a resistor with R is equal to 30 ohms and an inductor with L is equal to 0.600 henries are connected in series to a battery that has EMF 50 voltage and negligible internal resistance. At time t after the circuit is completed, the energy stored in the inductor is 0.400 joules. At this instant, what is the voltage across the inductor? So let us first know the given. We have the resistance, the 30 ohms, the inductance L is equal to 0.600 hertz henries. Then we have the battery EMF or the epsilon is equal to 50.0 voltage, and the energy stored in the inductor at the time t U is equal to 0.400 joules. So at this instant, what is the voltage across the inductor? So an inductor stores energy in its magnetic field. The amount of energy stored depends on the current flowing through it. So the energy stored in an inductor is this. Then in an RL circuit, the voltage across the inductor is in this. The VL is equal to L over T I over dt. So V sub L is equal to L over L times d I over dt. And then after that, we have this, the Kirch, Kirchhoff law rule gives. So this is the Kirchhoff laws. We have the epsilon is equal to IR plus V sub L. Then to find the current at its constant, since we are given the energy stored in the inductor, we first use the energy formula to find the current. So we solve for I. So I is equal is the square root of 2U is equal to over the L. Then all we need to do is to substitute the values. As you can see here, we need to substitute it like the I is equal to the square root of 2 times 0.400 over 0.600. So is I is equal to square root of 1.33, 333. Then square root of 1.333 is 1.15. Then copy the symbol or the ampere or the unit. So after that, we need to apply the Kirchhoff's loop rule. So the battery voltage is shared between the resistor and the inductor. So for the inductor voltage, we have this one. This is this is the formula to solve for the inductor voltage. Then after that, all we need to do is to substitute. So the V sub L is equal to 50.0 minus 1 minus times 1.15 times 30.0 is equal to 50.0 minus 34.5 is equal to V sub L is equal to 15.5 volume. So at this point, the answer is V sub L is equal to 15.5 voltage. So at this instant, part of the battery energy is stored in the magnetic field of the inductor, and the rest is being dissipated as heat in the resistor. So as time increases, the inductor voltage will continue to decrease. Current approaches its steady maximum volume. Then So let's try another problem solving. So we have the LRC series circuit. So an LRC series circuit has L is equal to 0.450 Henry. C is equal to negative point, is equal to 2 point to the power of negative F, and resistance R. What is the angular frequency of the circuit when R is equal to 0? B. What value must R have to give a 5.0% decay frequency compared to the value calculated in part A? So let us first try to solve in the part A, the angular frequency where R is equal to 0. We have this given formula. I mean the given in the problem solving situation, we have the L is equal to 0.50 Henry and the C is equal to negative 0.50 times 10 to the power of negative 5F. Did that. After that, when we have this, when resistance is zero, an LC circuit angular frequency. When resistance is added, the isolations are damped and the angular frequency decreases. So natural angular frequency or no resistance is this is the formula. The after this, um, the omega naught is equal to 1 over the square root of the LC. Then we have this damped angular frequency with resistance. So this is the formula. The omega is equal to square root of 1 over LC times R squared over 4, full 4 L squared. Then after this, we have to write the formula. So this is our formula. The omega sub is equal omega naught is equal to 1 over this c. Then after this, we have to substitute the values. So here is the values. The 1 over this the square root of 0.50 times 2.50 times 10 to the power of negative 5. So is equal to 1.25 times 10 to the power of the negative 5. And after this, we need to calculate this. So as you can see, here is the answer or the result. So given this is the final answer. So next is to calculate the fire resistance for a 5.0% decrease in the angular frequency. So we have this the 5.0 decreases means a new frequency is 95% of the original. So use of the damped angular frequency formula, we have to square both sides. So after that, after we square the both side, we need to solve for the R. So this is where it gonna goes. As you can see, then after we solve for the R, we need to substitute the values. So in substituting the values, we have the 4 times 10 to the power times 0.50 squared, then times 2.29208 squared. I guess it's 298 rather, squared minus 803 squared. Then after that, we have this equal to 4 times 0.22025 times 88804 minus 8089. So the r squared is equal to 0.81 times 8715. So the final answer is r squared is equal to 7059. So after that, after this answer, we need to after we come up with this answer, we need to take the square root. So after we take the square root, here is the final answer. As you can see, it's 84.0 ohms. So this problem shows that resistance reduces the oscillation frequency in an LRC circuit. Even a modest resistance can noticeably lower the angular frequency. When resistance becomes too large, oscillations eventually disappear entirely, turning the circuit into a non-oscillatory system. Then for the summary, in summary, this chapter shows how changing electric currents and magnetic fields are closely linked through the principles of inductance. Mutual inductance explains how a changing current in one coil can induce an EMF in another, while self-inductance describes how a circuit resists changes in its own current. Inductors store energy in their magnetic fields, which plays a key role in the behavior of RLC and RLC circuits. In RL circuits, current changes gradually due to inductance, while LC currents allow energy to oscillate between electric and magnetic forms. Finally, LRC circuits demonstrate how resistance affects oscillations, leading to either sustained damp or no oscillations, highlighting how inductance is essential in controlling current, energy flow, and signal behavior in real electrical systems. So that's all. Thank you.